What I want to talk about today is kind of the third in our sequence of how to draw a straight line between two sets of points, right? This thing is called support vector machines. Or SVMs. So, like I said, we've seen several different ways now of drawing a hyperplane between two sets of points for purposes of classification, right? And we talked about Fisher's linear discriminant, we talked about logistic regression, and now today we're talking about a different method. The way that all these methods differ is in their specification of the cost function, which is basically saying what makes a good hyperplane, what makes a good line, okay? And so kind of the idea here, the motivation for this particular idea is that there are many straight lines that can divide linearly separable data. So what I mean by linearly separable is that the data is possible to totally classify correctly. Right? So suppose that I have, a set of points over here, and I have a set of points over here, right? There are a lot of ways that I could draw the line, right? I could draw this line, I could draw this line, I could draw this line, right? So, which one should we choose? In some sense, which one of these is the best line? If we're talking about, classification error, all these lines have zero classification error. So there's really no basis on the error alone for making the decision, okay? And so the proposal behind support vector machines is that what we want to do, and I'm going to say this on the paper, but just in words, is we want to minimize the, okay, so we're trying to, all right, let me write it down first so I don't mess it up. So the idea of SVMs is that we want to maximize the distance of the closest point to the decision boundary. Right? So if I look at my picture again, here, sorry, well, let me just redraw the picture. So let's suppose that I have X's and O's instead, okay? So kind of what I want to do is to say, okay, what is the best way to draw this line, right? Well, if I drew a line that was kind of like too close to this red O, for example here, this would do a good job, but the closest point to the decision boundary would be very close, right? I clearly have some leeway over here on this side, right? So instead, I can imagine doing something like this, right? Where I say, okay, I'm going to draw like this line, and then if I think about the closest points, I've got this distance, this distance, this distance, that all three of these distances are the same, and that kind of minimizes my distance. Again, I'm measuring this perpendicular to the straight line, right? So what I'm trying to do, in some sense, if you imagine that you're kind of like, driving fast through an obstacle course, what you want to do is you want to stay as far as possible from both sides of the road as you can, right? So you're trying to center yourself along the road. And so this distance between the closest point and the decision boundary is called the margin, right? So this distance is called the margin. And so what the SVM is trying to do is to maximize the margin, okay? So I don't want to have like the dotted line, which is like, got a very small margin. I want to try to push that line to kind of be just like right in the middle so that I draw these right angle lines from the two sides and those numbers are both the same, right? So the idea is that if I do this right, the numbers on each side of the line are kind of balanced. And then, the nice thing about a support vector machine is that once I've figured it out, I don't need to keep all the points that are far away from the classifier, right? In some sense, none of these other points here play a role at all in the decision boundary. It's only the ones that drive where that line is, right? So in terms of, kind of a compactness argument, it's kind of nice to say that I could, add a whole bunch of points over here and a whole bunch of points over here, nothing would change, right? And again, we were talking about robustness last time, or a time before, about one problem with linear regression is it's robust to outliers, or it's not robust to outliers, right? So if I had some points that were way out here and I was doing regression, that might tilt my line. In this case, I'm not going to have that problem because those guys are not going to be support vectors. And so, kind of the only thing I care about are these points here. And I'll also say that the points that define the margin are called support vectors. Okay. So that's the kind of the setup. That's the picture. And let me just say in advance that, support vector machines prior to the kind of whirlwind of deep learning were for a long time kind of like the best game around for classification. And there's also a version of this called support vector regression, right? So this is kind of why I'm teaching it in this class. I will have to be honest, though, to say that many people are not using support vector machines anymore because they've been kind of overtaken by neural networks. And we'll talk about that after the exam. But I think it's still worth knowing the concept, how you derive them, why they're useful. And there's especially an important idea at the end of this lecture called the kernel trick that is kind of important to know more generally. And so again, I'm sure that if you're going on some sort of a LeetCode code interview, that someone's going to ask you one time in your life about support vector machines. So that's why I want to talk about it for one lecture. Okay, so questions about the setup. Okay, so let's figure out how to actually find this line and determine the support vectors. Okay, and this in itself, I think, is a good mathematical exercise to kind of test your understanding of calculus, to recollect those things like Lagrange multipliers, which we're going to talk about. So here's the formal setup. So the idea is that we have n training samples. And again, we have our usual setup where I have the input and the target vector, right? And this time, and I'm going to make a switch from last time. So here, I'm kind of explicitly labeling the target vectors as -1 and 1 instead of 0 and 1, okay? It turns out that will make life easier later. And so we want to design a classifier of the form y of x equals some weights transpose. And here today, I'm going to use this phi of x again. So remember that this phi of x is basically like a feature, vector, which could be a transformation, a nonlinear transformation of the original variables, right? So if I just want to use the original variables, then this is just x, right? But if I want to allow for nonlinear things, then I'm going to just have this phi of x, okay? That's, to kind of fit in with our derivations of other things we talked about in this class. So again, this could be nonlinear. And again, this here is the input. This here is the target. And these are the labels, right? Okay. And since I've tried to keep this +1, -1, then our classifier's output is going to be basically the sign of the result. So if I run my input through the feature vector and I look at y of x, if it's positive, I choose the +1 class. If it's negative, I choose the -1 class, right? So the classifier's output is basically the sine of this y, right? So if this number is greater than 0, then I choose class 1. If this number is less than 0, then I choose class minus 1. And if it's exactly equal to 0, then I just flip a coin. OK. So there's my model. And so now how do I phrase this idea of trying to maximize the margin? OK. So the cost function, or maybe a better way to say it is the optimization problem. We want to optimize the maximum margin. So it's like saying I want to maximize the minimum distance between. All right, so let me just write this down here. So here, this is like saying this is the distance of point I to the decision boundary. And technically what I mean by this is, phi of x of I. Right, so I want to find the minimum over all the data points, and I want to maximize that minimum over all the possible linear parameters. And I want to constrain this optimization, right? So what I'm trying to also say is that I want all the points to be correctly classified, right? How do I kind of write that down? So I'm going to have a second category such that Ti times this thing is greater than or equal to 0 for all I. What is the meaning of this? So again, this is like saying this is the true sign of the output. This is the model sign. This is like saying that if the true sign is -1, I want the model sign to also be -1. So this product is positive. If the true sign is +1, I want the model sign to return +1, so it's positive. So this is just a way of saying that all points are correctly classified. And it's kind of a nice compact way of saying that. So this is a little bit different than what we've seen so far in the sense this is what's called a constrained optimization problem, right? I have a cost function. In this case, I'm trying to maximize this value, so it's more like I'm maximizing an objective function. And I also have these constraints. And so that's going to be a little bit trickier to deal with mathematically, and we'll talk about how we do that as we go on through the lecture. Okay, so now what I want to do is figure out, well, what is this actual distance value, right? How do I actually kind of measure that perpendicular distance, right? So let's take a look. So what is the distance of the point to the hyperplane W transpose blah, blah, blah equals 0? So it's like saying, if I kind of dumb this down into 2D, it's like saying, OK, here is my hyperplane. This W is the vector pointing in this direction, perpendicular to the hyperplane. And if I have some point out here, phi, well, this perpendicular distance is kind of like saying, OK, I can drop down and project phi onto the hyperplane. I get some value z. So basically, it's like saying that this vector is z plus the perpendicular distance, right? So phi of xi is like z, and let's call this number r, plus r, and I'm traveling along this distance, and the vector that I'm traveling along is basically related to the weight, right? So this is like saying, I want to travel in this direction, and I'm normalizing it, so this thing here is a unit vector. And then r is the actual distance that I want. Okay. And so now let's see if we can figure out this r more explicitly in terms of all of our variables, okay? So I'm going to move some stuff around. I'm going to say that, okay, now what I have is that, how did I get phi in the first place? My phi is, or this is like saying that, okay, what I want is that I'm going to multiply both sides by W transpose dot plus B, okay? So on the left-hand side, I have W transpose phi x of I plus B. On this side, I have W transpose Z plus R, W transpose W over this plus B. And now I can make some simplifications to say, oh, well, by definition, this thing here, W transpose Z plus B is 0 because that point is on the hyperplane. So here I can say that, W transpose Z plus B equals 0 since Z is on the line. And then I can rearrange things to find out what R is, right? So now if I say, okay, this part drops away. Also, this thing here, W transpose W, is just like the norm of W, right? So here, this thing here is the same as the norm of W squared. So I can kind of make a simplification there too. So what I get is that moving stuff around, that if I want to get R by itself, I have R equals this part, which is W transpose this, over, I've got an extra factor of this. And I also have a absolute value here just because I want my distances to be positive, right? So I have an absolute value, distances should be positive. So I take the absolute value. And kind of one way of getting around this is to say that, I can actually multiply this top part by the label, right? So if this number is 1, then this guy here should also be 1. If this number is negative, then this label is also going to be negative. So I can kind of pull it all together like this. Okay. And so now I can go back to my slide a couple pieces ago and say, okay, I'm going to substitute in this thing for what we said R was. So we want to maximize basically I want to, maximize over the set of possible parameters the minimum distance, which I now know is this quantity. Or maybe, yeah, well, this is fine. I mean, technically, I want to optimize or I want to solve this problem, right? Subject to the constraints that I had before. So one thing here I have to address to make this work is that there is a kind of a scale ambiguity to the way I set up this problem, right? So what would happen if I multiplied W and B by the same constant, right? So suppose I'm going to say there's a scale issue. If I have the, AW and AB, and I plug these in, then what I have for my guy here is this will turn into 1 over norm AW TI AW transpose this thing plus AB. These A's basically cancel out, and I have the same cost function, or the same value, right? So kind of what this means is that, I kind of need to define a scale for W and B in order to not prevent these things from, messing up my minimization. So kind of what I'm doing is I'm saying, okay, I've got to, set some sort of a uniform scale on how I'm finding the result. And so the easiest way to do this is to say that I am going to enforce that I scale my W and B such that the distance of the closest point to the margin is 1. Okay, that's going to make life a lot easier, because then this minimum number here is also going to be 1, right? So what we're going to do is, convenient scaling is to set W transpose times its phi plus B equals 1 for the point or points closest to the hyperplane. That's like saying, I'm going to tell you that I want you to set this problem up in such a way that the margin equals 1, and all the points then that are not on the margin are further away than 1, right? So that's like saying that the margin is equal to 1, and all points are at least 1 away from the line. That makes life much easier, right? Because what that means is that this number here totally drops away, right? It's like saying that, this makes the problem much easier. This is like saying now, okay, I want to maximize just this thing subject to the constraints that I had before. So now this is looking like a little bit more tractable, okay? And kind of alternately, if I want to make this a little bit easier, if I want to maximize 1 over something, equivalently, I could say I want to minimize this thing, right? So here, it's like I'm trying to drive the denominator as close as possible to 0. Here, it's like saying, okay, I want to drive the numerator as close as possible to, so maximizing that, right, is the same as minimizing the norm of W, right? I want to make the norm of W as small as possible. So if we're going back to our world of like minimization problems, this is an easier way to think about what this cost function is. And so this kind of cost function, this kind of optimization problem, is a known thing that's called a quadratic program. So this type of problem is what's called a quadratic program. Now, lest you be like freaking out about, is he going to ask us to do this stuff on the exam, or am I going to have to code this up? The answer is no, right? This is all kind of for your information. I want to show you how this problem is solved, but when you do this in practice, you would just call a quadratic program solver to do it. You wouldn't have to think about the implementation details yourself that much, okay? The nice thing is that, the objective function is the square of the weights. So this is a quadratic thing. This is also linear in the weights. So basically, I feel like I'm going to sneeze. Ooh, excuse me. So basically, when I have something that's quadratic in the objective function and in the constraints, then life is called a quadratic program. The nice thing about this is that it has a single global minimum. So again, this is nice. This is a convex cost function. So life is good, right? So this has a unique global minimum. Can be found with, software packages. What you look for there is what's called, a quadratic program optimizer, right? There's stuff built into MATLAB, built into Python, and so on. And so when I go through this process and I find out, okay, which of the constraints are exactly equal to 1, those are the ones that are going to correspond to my support vectors, right? So whenever you solve a constraint optimization problem, you'll find that at the end of the day, one of the constraints is going to be binding, right? So I'm not going to have all these values exactly greater than 1. A couple of the values will be exactly equal to 1, right? Otherwise, I could do better by changing the weights. So after optimization, what are called the active constraints, which is the same as saying that this number here equals 1, give the support vectors. And so that's the basic idea. Okay. So I want to talk about how to actually solve this problem, right? So I will go into how it works. Before I do, though, I want to say that not every problem in the world is, actually linearly separable, right? Meaning this is kind of a setup in the case that I can actually draw a straight line that divides the data, and I'm just trying to find the best straight line among a whole family of ones that will work, right? On the other hand, in the real world, there may be too much of a mix of the classes, meaning that I'm just trying to draw the best straight line that I can. And I can still talk about what support vector machines mean in that context, even if I can't divide the classes exactly, right? So this is great, but in the real world, data is often not linearly separable, which means that some of these constraints here, will be violated, right? I can't get all the points to be correctly classified all the time, okay? So conceptually what this means is I still have an idea of a margin and trying to maximize the margin, but now I'm going to let some bad points kind of stray into the margin, right? So conceptually, this means that some points will kind of end up in the margin. But I want the number of those bad points to be as small as possible. And I want their intrusion into the margin to be as minimal as possible, right? So I'm still trying to do the best that I can. So let me kind of illustrate what I mean by that. So kind of a situation like this, again, X's and O's. So let's say something like this. Right here, it's not so easy now to draw the dividing line, right? Because of this extra O over here. And I'll show you an example in a moment that is actually numerical, right? But let's just think about what would the dividing line look like, right? So it's kind of like saying, okay, I will try to divide these points as well as possible. But I may not do the best job, right? So here, I still have kind of like some vectors that control the situation, right? So the margin in this case may look like, this. But there are some points now that are on the wrong side, right? So here, this is the line W transpose phi x phi x plus b equals 0, right? Here, this is the positive side of the line. This is the negative side of the line. And so what I'm going to do is I'm going to define what's called a slack variable that tells me how much violation there is for a given point. So first let me talk about mathematically, and then I'm going to come back to this picture, okay? So that's like saying that instead of my constraint looking like this, TI. Right, this was my kind of before constraint. This is like saying that every point has to be correctly classified, right? Now what I'm going to do is I'm going to, allow what are called slack variables. And again, if you've ever taken an optimization class, this will be familiar. And if you find this stuff interesting, then you should take an optimization class, right? So this is like something you talk about for a full, lecture in Intro to Optimization. So now what I'm going to do is I'm going to say, okay, you don't have to be exactly greater than 1. I will let you be greater than 1 minus some number where this number is, positive, right? So if Sn equals 0, then I've satisfied the constraint. If Sn is greater than 0, that means that my constraint is not exactly satisfied compared to this one up here. Okay. So basically, points with this Sn in the range of 0 to 1 are still going to be, are still going to be on the right side of the boundary. So they're going to be okay. So these will be correctly classified. But points with Sn greater than 1 are going to be misclassified. And so you can kind of see maybe where this is going, which is to say, now what I want to do is I want to minimize the amount of misclassification, right? So ideally, I want Sn to equal to 0, right? If Sn is small, I'm okay, but not not great, but it's okay. If Sn is greater than 1, then I'm going to have misclassifications, right? So what I kind of want to do going forward is I want to minimize the objective function plus some multiple weight times the sum of the SNs. Yes? So these SNs are what are called slack variables. Right, so for every point, I guess I should call this SI, maybe. Sorry. Right, this is basically saying how much does every point violate the constraint. Start with that. So basically, the slack variable here, so if I look at this is like saying that, okay, let me just draw this a little bit better. So like here, this is a situation where, I have correctly classified the point, but I'm inside the margin, right? So here, this would be like a point where S is, in the range of 0 and 1, right? This is a point where I have misclassified the point, right? So this point, S will be greater than 1. And what else have I got? I guess this also is a point where this S is greater than 1. Everything else is correctly classified and inside the boundary, right? So all these guys have S equals 0, right? Everything is good. So kind of the idea is that the dotted lines are the danger zone, right? So the closer I get into the dotted lines, now I penetrate into the margin, I want to minimize those points, either misclassified points or correctly classified, but not great, right? So the further that this O pushes into X territory, the higher the S is going to be, right? And so now the thing I want to do is to modify my cost function to say the following. And now it's a little bit, back to being a little more complicated. So I want to say I want to minimize my original function plus lambda, which is kind of like a tuning factor, times the sum of the slack variables. And I want to do that subject to the constraint that I'm trying to achieve correct classification as well as I can. So basically, lambda controls the trade-off of how big the margin is and the amount of violation I will allow, right? So, that's something that we will, kind of be able to tune, right? But that's the idea, right? So I'm going to basically set this system up, and those of you that have, well, even you may remember from like vector calculus, right? You had to solve these problems like minimize the volume of an ellipsoid that you can fit inside of a box, right? So that was like a classic Calc 3 problem. That's a Lagrange multiplier problem, right? Where you've got some constraints that says the ellipsoid has to fit into the box, and you've got the objective function, which is the volume of the ellipsoid. And how do you solve it? You create what was called a Lagrange multiplier, which is what this lambda is, right? So I'm going to kind of try to take a few steps towards solving this problem in a minute. But the main thing is that I wanted to kind of like pose what is the, what is the setup? And so the other thing I wanted to kind of say, this is a good point to mention it because we're going to come back to this after the exam, is that this is like an example of what's called hinge loss. We'll say more about that when we talk about neural networks. But the idea is that we, don't care about correctly classified points far from the decision boundary. Oh no. So the idea behind support vector machines in the first place is that, if you're correctly classified and you're far away from the margin, I don't care about you, right? Nothing that you do and move around will change what I think my classification should be. But those of you that are close to the boundary, I'm going to pay more attention to, and I'm going to penalize the cost function, right? Okay. So this is the setup for slack variables, right? And again, you would solve this problem in a way that's similar to what I'm going to tell you about next. But kind of in some sense, what I want to do is just go back to the world of no slack variables. Like, let's suppose that everything was linearly classifiable, then how would I be able to find the answer? Okay, so let's go back for a second to, let's assume that everything is linearly separable. That means we don't need slack variables. Oh no, this pen is dying too. I may have to switch to a red pen, right? So the kind of setup is that, the problem looks like minimize some function subject to some other constraint, some other function, right? Or something like this. So this type of function, again, is what you solved in calculus using Lagrange multipliers, right? So the idea is that we convert this into, so this is what you call a constrained optimization. And instead you convert this into an unconstrained optimization by saying I want to minimize over x and this lambda function, this lambda variable, f of x plus lambda g of x, right? This is called the, Lagrangian. And then once I have no constraints, I solve it in the usual way by saying, okay, I want to minimize over both x and lambda. So if I call this thing, L of x and lambda, then what I do is I try to take the derivative of x set equals 0 and the derivative with respect to lambda and set equals 0, right? That's the general solution path that maybe you mistily remember doing once upon a time when you took calculus 3, right? And so how does that apply to our problem, right? So our problem is basically like saying, okay, let me, apply to SVMs. So it's like saying my cost function is going to be a function of the weights and let's call them AI. These things I'm going to call the Lagrange multipliers. I have the cost function, which I had before. And then I'm going to have a term that corresponds to each of these numbers here. Now I know things are getting a little bit hairy. Just let the math wash over you. All right, this is basically like saying, here is my constraint. I have n of them. And then I have kind of like the, lambda in Lagrange multipliers, right? And so now what I would do is I would have to take a bunch of derivatives, right? I'd have to take the derivative of this with respect to w and set it equal to 0, right? If I did that, I can actually do that more or less here. It's like saying that I have, w is here, because it's like w transpose w. And then I have, on the other side, I have the sum. W appears over here multiplied by phi. So I'm going to have this here. If I take the derivative with respect to the bias, then what I have is, there's no b here. The b over here is only multiplying a times t, right? So this is like saying that I have this sum equals 0. So why is this important? What this is telling me is that I could basically substitute in, if I knew what the optimal A was, then I have W in terms of that A, right? Because everything else I know. I know the T's, I know the P's. What I don't know are the A's. So if I knew the optimal A's, then that would also tell me the optimal W's. I could work backwards to get the optimal B's. So kind of what I can do is I can rewrite this whole thing into a cost function that only depends on the A's, which is kind of nice. So there is a little bit of manipulation, but the nice thing is that can rewrite solely in terms of the A's. What would that look like? Well, for example, I can plug in this whenever I see a W, right? And the upshot is that the new cost function looks like the sum of the AI minus this double sum The only reason I'm doing this is to get to this critical point at the end here. So here, this is still a quadratic program, right? Because it depends on the A's only, in terms of linear terms and multiplying them against each other, right? So this is still a problem that I can solve. I need to solve it numerically, but it's not hard to do, right? The key idea here is that I have this thing at the very end, right? This is the only place now where the original x's are coming into the equation at all, right? So this is basically like the, taking the feature transform of each of the points, getting that vector and transposing it with this other thing, right? So the key idea is that, I'm going to call this k xi xj. And the reason I want to do this is because we'll come back perhaps to this kernel idea later. We have this idea of a kernel function. Defined as the relationship between two data points is this quantity here. So if I just use the original feature vectors, this would just be like xi transpose xj, right? Okay. So let me kind of try to bring this all together here. So the reason I care about this is that now, if I could tell you this function, and here, this is just like, since I have n data points, this is basically just kind of like an n by n matrix, right? Because I'm taking a vector transpose another vector, so I'm going to end up with basically a dot product between the feature vectors, right? And so the whole problem is kind of coming down to this one matrix that is called the kernel function, okay? And the cool thing is that if all I told you was this set of n by n numbers, I wouldn't actually need to really take the feature transform at all, right? Like I wouldn't actually have to form this pair of phi vectors and take the transpose, because I could just tell you, okay, this is just some function of x and xi and xj, right? And that's where SVMs really showed their worth back in the day, which was this idea of using a kernel function that kind of specified nonlinear features in feature space that you as the user didn't have to think that much about. Okay, so the advantage is, let me try to write this down. So the advantage here is that we don't really have to think about features at all, just the, function that's specified by the kernel. So for example, I could say, the kernel is equal to xi, transpose xj, right? Here, this is just like the original features. If I said that the kernel was xi transpose xj plus some constant to the m power, this is like implicitly getting the polynomial basis all the way up to m, right? So it's kind of like saying I have the polynomial basis up to, the mth order. Or I could say something like this, the kernel, which again is kind of thinking about like a distance between the two vectors, right? I could also say something like this. This is like a Gaussian kernel. And it turns out that this is kind of like saying, as we know, I can get a better and better model by increasing the length of my feature vector, right? So I could do it better with a cubic polynomial than I could do with a quadratic polynomial, right? And the advantage here is that this Gaussian kernel, turns out to implicitly, have a feature set with kind of infinite dimensionality. I'm not actually specifying what the features are anymore. I'm just specifying how this kernel acts on the features, right? So in a way, I've totally removed the phi from the equation at all in favor of specifying this kernel, okay? And so I know it's kind of hard to grok the first time that you see it, but with a little bit of reading, hopefully this will kind of become familiar. This is kind of called the kernel trick. Sometimes you see in the machine learning literature. The idea is that you don't have to, define your features. Instead, you define a kernel. And often, defining the kernel is very easy, and you get more powerful features at the same time. So it's kind of like a win-win. So, and then once you have, solved your problem, then you can apply the kernel to some new point just by basically, plugging in the x that you care about, right? So for example, to apply the kernel SVM to new data, we need to compute just these numbers, right? This is my new data. And these are my training vectors. And at first, it seems like it's a pain to keep all of these training vectors around. Suppose I have like 1 million training samples. Does that mean I have to compute 1 million numbers every time I want to evaluate the model? The nice thing is that I only have to do this for the few support vectors that I have. Because it turns out that those are the only things that matter, okay? So kind of let me show you an example of this with real data, just kind of give you some sense of how this works practically. So here is just a set of examples I put together. So let me trash this guy. And again, I just put this together in MATLAB. No. So if I say linear kernel. Right, so here's the classic example of a SVM, right? The black and the red points are well separated, and I can kind of see that this dividing line, the one in the middle, nicely splits the data in such a way that the distances of the circled points are exactly the same as I go towards that line perpendicularly, right? It shouldn't be hard to convince yourself that if I were to try to tilt that line left or right, it would end up being closer to one of the points, right? And so this is the best that I can do, is kind of like driving right down the middle of this lane created by my data, okay? Now, when life is not so separable, then I'm kind of in a situation like this. So here's a case where I have red and black points, but I can't draw a single line that goes between them, right? So here, what I have instead is, think about it, all the circled points are playing a role in terms of being support vectors, right? So basically any vectors that are inside the margin are support vectors, as well as any misclassified points. So what you see here there are some points like, I can't unfortunately zoom in on this picture the way I've got this set, but like these black points and this red point are right on the dotted lines. But then there are a whole bunch of points that are inside, and some of these points, like the red points between here and here, these are all correctly classified, but they are, within the margin. And then I got some black points here that are misclassified, right? Because these guys should be on the other side of the line. Similarly, I have a couple of red points that are on the wrong side of the line, and a bunch of black points that are inside the margin, right? So this is the more typical situation that you have when you can't linearly separate the data. But the idea is that to evaluate the model, all I care about is what's going on at this handful of points. And even though there are, I don't know how many, like 50 or 60 points in this data set, only this 15 points are what are controlling the model. And life is even better in the other case I showed, where no matter how many points I have, it's really only these 3 points here that I ever have to evaluate, right? No matter how many points end up getting added to either side of the line. Now, if I change the kernel, right, and if you use a SVM package, you will find out that it's just easy as just changing a flag somewhere in your package, right? So if I change my kernel to, say, Gaussian kernel, then the decision boundary, let's actually do a quadratic kernel first. So if I use a polynomial instead of a straight line, then this is what I get. Now you're going to say, well, it looks like this straight line is closer to these points than it is to that point. But the thing you have to realize is that I'm talking about doing this in the space of quadratic functions, right? So I'm taking the features and I'm using this phi function to push them up into quadratic space, and then I'm finding the discriminator and then pushing that back down onto the original feature space. So the support vectors are still kind of the ones that are closest to the decision boundary, but they're a little bit harder to interpret, right? If I do it with Gaussian kernels, it's even more goofy. So that's what I showed initially here. So here, if I use a Gaussian kernel, then the decision boundary looks kind of like this red cloud over here. And again, the support vectors are a little bit harder to interpret here. It's the ones that are kind of on the boundary closest to the cloud, more or less. The black ones are really hard to interpret. But the idea is that I can create these decision boundaries that are not straight lines at all, right? That's the take-home message here, is that the SVM kernel decision boundaries can really look very different than normal decision boundaries, right? So I think I have this example for the other guy. I'm not sure what this looks like. Right, so here, the decision boundary is more like a curve that goes through here, right? So there are definitely cases that are not linearly separable, but that may be separable in the higher up kernel space, right? Unfortunately, I don't have a great example of that right now. I'll try to prepare one at some point, just so you can see that it is theoretically possible that you can kind of like make these decision boundaries wrap around weird spaces. Yeah. So the kernel part is basically saying that I'm not actually doing the distance measurements in this space anymore. I'm doing them in some very high dimensional feature space, right? And in theory, the high dimensional feature space lets me do a lot more than just a straight line, right? But when I find the straight line high dimensional feature space and project it down to the original feature space, it's going to turn into some perhaps very squirrely, interesting looking shape, right? So it's possible that my decision boundary could wind its way around all the points in an interesting way, right? Or I could have like islands of different points that are classified. I know it's kind of hard to kind of get an intuitive flavor for it, especially the nonlinear kernel stuff is really hard to wrap your mind around the first time you see it. So if you don't quite follow what I'm talking about, don't freak out. Yes?
Same question about, so not like one distance in a higher dimension. It's just some. Is it like a covariance distance, or like what is the? Like
So the kernel function is implicitly specifying the distance function in a way, right? So here, this is kind of like, yes, that's kind of like the way to think about it, right? Is that, I'm still computing distances to hyperplanes way up in this nonlinear space, right? But those distances are no longer linear down in the original feature space, right? And the kernel is implicitly kind of specifying that situation, right?
Like the Gaussian case, the distance is the e to that's the distance. Right?
Well, this is kind of like maybe it's more proper to think about like a radial basis function, right? So like here, this is kind of like saying that I have a radial basis function centered at each of the xi's, right? That's kind of maybe more accurate to say, right? So yeah, this is a little bit kind of hard to explain. I'm really giving you the very top level bulletin of all this stuff because to understand the kernel, to understand the Lagrange multipliers, I have to do a lot more digging into optimization theory and so on than I would like to do just in this intro class, right? If I want to give you the takeaway, right? So the main takeaway I want to get is that, right? So for linear classification, I have a bunch of options, right? So I have Fisher's discriminant, which is basically like this idea of what's called LDA. That's kind of assuming that the classes are Gaussian and trying to minimize the within class scatter and maximize the between class scatter. Right? I'm trying to find a projection such that those things are as well separated as possible, right? Then you have logistic regression, which is basically, the better thing to do because it gives kind of like a probabilistic class membership. Right, so via this softmax function, we can look at the results of logistic regression and interpret the results as the probability that a point is in a given class, which often is very constructive. And then for SVMs, the cost function is basically to maximize the margin, right? These are all just kind of like three different perspectives on the right way to draw the line. And the last one we're going to talk about after the exam is called the perceptron, which is, so after the exam, the perceptron, which is the thing that we talked about very briefly at the beginning of the first lecture, talking about the New York Times article about the invention of the perceptron, right? This is also a way of drawing a linear decision boundary, but again, we're going to do this in some high dimensional space that is defined by a neural network. So, these are the kind of basic, take-home messages. I'm not expecting you to program the SVM, to minimize the SVM. I think it is useful to apply the SVM, right? So I think what I'm going to ask you to do on the third homework is to look at a classification problem and then show me the decision boundary that you get with a line that you compute with the SVM. Then you should be able to see the margin and the points that define the margin. And then if you try the Gaussian kernel, you should be able to see that the classification error can be made much less, right? Which corresponds to some nonlinear decision boundary. I think that's the lesson here, is that you can always do better with a nonlinear decision boundary. The question is, what is the right way to construct it, right? And so SVMs with a nonlinear kernel are one way of doing that, and then neural networks are a whole different way of doing that. So we're going to talk about that later. Okay, so yes. Reading the section in Bishop on support vector machines, I think is a worthwhile thing to do to, again, look at the pictures, get the intuition. It has all the details about how to do the Lagrange multiplier minimization and so on that I kind of glossed over. And like I said, I think that SVMs are important to know about from the perspective of what are they trying to do, right? And again, I can very easily imagine someone will ask you on an interview, like, what is the idea behind an SVM, even if no one is using them as regularly as they used to. I can definitely say that when I started out as a professor 20 years ago, SVMs would be like the natural thing to try for a machine learning problem before everyone jumped to deep learning and now transformers, right? So, okay. So questions or comments about this? All right. So that's the end of this lecture.